Today we're going to look at mean value theorem for derivatives. What the mean value theorem says is if you have a function f of x and it's continuous over an interval a, b, and also differentiable over the interval a, b, which means you can find the derivative at all the points, then there is some point c in between a and b for which this statement is true. The derivative at point C is equal to the difference in the function of f over the difference in the interval. So we're going to look at how this mean value theorem, what it means for functions, how it applies to different equations that we're going to be looking at. So we're going to need to know a couple things when we're doing this. What's the interval? Is the function continuous, which means you can trace the whole function. There's no asymptotes, there's no holes in the graph, those types of things. It's differentiable. There's no points where you can't find the derivative. And remember, we talked about those types of things, such as there's no corners, can't find derivatives at corners, there's no cusps. It is the places where it's not continuous, obviously there won't be a derivative. And also that there is no corners, cusps, or where it's not continuous, or no vertical asymptotes. All right, what does this mean value theorem really mean? The mean value theorem says that basically that at some point in the interval, the actual slope equals the average slope. And kind of keep in mind again that the mean value theorem only applies over a closed interval. So it means at some point the actual slope equals the average slope. Here's what that looks like here. This is your actual slope. Remember, derivative finds slope. This is just function notation for the slope formula. Remember the slope formula that you've done before, y2 minus y1, x2 minus x1. It's just a fancy way of writing the slope formula in function notation, but this is the average slope between 2 points. So basically this formula says, where does the actual slope equal the average slope? Let's look at it on a graph and kind of see what it means. Here's an illustration of the mean value theorem. There's this blue function here, f of x, that's drawn out. Over the interval from a to b, so if we trace that function up from here to here, this function is continuous. Also, it doesn't have any corners, cusps, vertical tangents. It's continuous, so it is also differentiable over that interval. So the mean value theorem applies. And the mean value theorem says the average slope should equal the actual slope. Well, let's first find the average slope. If we were going to find the average slope between A and B, we would want to find what's the rise over run. So the rise over run would be whatever the function equals at B minus whatever the function equals at A, which would be point B and point A here, minus the difference of the x's, your run, B minus A. And that would give us this line. Here's the slope. Here's the average slope right here. That's the average slope for the function between A and B. What is the actual slope? The actual slope would be the derivative at a certain point. And at point C right here, if we follow it up, if we were to find the tangent slope at C by finding the derivative, that's the point that hits the curve one time, tangent slope. That slope is parallel to this slope. And that's the point where the actual slope is the same as the average slope. So you're guaranteed to have one point like this over an interval if it's continuous and closed, where the actual slope equals the average slope. The lines are parallel. All right, so in this first problem, we're going to look and see if first if the mean value theorem applies to this function right here, y equals x squared on the interval from 0 to 3. We want to first see, does this satisfy mean value theorem? Remember mean value theorem, it says has to be in a closed interval. Is this a closed interval? Absolutely, the brackets mean that we're closed. This right here is saying that x has to be less than or equal to 3 and greater than or equal to 0. That's what this is saying here. So yes, it is closed. We count the endpoints. Also, it has to be continuous. Is this function going to be continuous? Absolutely. X squared, it's a polynomial, second degree polynomial. There's not going to be any bad stuff in this one. There's no way we can get division by 0, square roots and negatives, that kind of stuff. The domain is all real numbers, so yes, it is continuous. And finally, is it differentiable everywhere over the interval? Well, is it differentiable? Let's find the derivative of this one. If we find the derivative, it would be 2x. Is there anywhere between 0 and 3 that we would get a bad derivative? No. If you look at our derivative here, that would have a derivative everywhere between 0 and 3. Just to make sure, let's look at the function. Let's graph it out, and just to be on the safe side here. X squared, if we graph that out, between 0 and 3, we can see, yep, it is continuous, it's closed, it's differentiable. All right, so let's apply mean value theorem now. What is the value for this one that satisfies the mean value theorem? We want to figure out where's this point right here, C, that makes the actual slope equal the average slope. All right, so first thing we got to do is plug in what we know in this equation. A and B in this equation would be the endpoints here of our interval. So A is going to be 0, B is going to be 3. So on this side, we know on the bottom we got 3 minus 0. On the top, what is the function at B? What's the function at A? That should be easy to figure out. Our function at A would be what we get when we plug 0 in here. So what is y at 0? What do we get when we plug 0 in? 0 squared is 0. Also, what are we going to get when we plug 3 in? 3 squared is going to equal 9. So on the top here, our function at 3 is 9. Our function at A, or our first point, is 0. All right, now we got to put that equal to the derivative. What's the derivative? Well, we already found the derivative of this function is 2x. So what we're going to try to do is figure out what is that x? What's that value that makes these equal? All right, so let's simplify the right side. If we simplify the right side, on top we got 9, on the bottom 3. If we keep simplifying, 9 divided by 3 is 3. So we get 2x equals 3. Dividing by 2, then we see that at 1.5, or at 1.5, that is where the actual slope equals the average slope. So at that point, the slopes should be the same. We should get the same slope at each point. Just to show it works here, what did we get for the right side here? The actual slope between these 2 points was 3. If you find the tangent slope, plug this 1.5 back in for here, you would also get 3. 2 times 1.5 is 3. So yep, the actual slope equals the slope. If you look at the graph on this one, if you graph x squared out, there's a point at 1, 1, 2, 4, 3, 9. Looks something like that. If you graph it out, the average, so what it's saying is the slope between here and here was a slope of 3. And it's true, if we look at it, it's going up 3 over 1, up 3 over 1. Up 3 over 1. So yep, that's the average slope. What's the actual slope? They're saying at 1.5, at right here. The tangent line also has a slope of 3, and it's parallel to this one. So that's what mean value theorem says. Let's try it on another one here. On this one, show that the function satisfies the mean value theorem. Okay, again, we got to check, does the mean value theorem apply? Is it a closed interval? Is it closed? Yep, we can see we have or equals 2 lines there. Yes. Is it continuous over the interval? All right, is it continuous? If we graph this one from 4 to 9, is it continuous? Well, let's take a look and see. Let's put this function in and look. Natural log of x minus 3. Well, you can see this graph starts at a value of 3, because if we put 3 in here into this function, there's not an actual value at 3 itself, because 3 minus 3, that'd be ln of 0. Can we do ln of 0? No, you can't do logs of 0 and negative. So 3 itself, the function doesn't work there, but the domain of this would be that as long as x is greater than 3, this function is continuous. So is 4 through 9 greater than 3? Yep, so this one's continuous. All right, the last thing, is it differentiable everywhere? Well, differentiable, we got to check. What's the derivative? What's the derivative of this one going to be? Derivative of ln is always 1 over whatever you're taking the derivative of, x minus 3. And we got to do chain rule. Derivative of the inside derivative of x is 1. Derivative of 3 is a constant, so it'd be 0. So this would be times 1, or just 1 over x minus 3. Is this one differentiable everywhere? No, this one's not differentiable everywhere. There is one point where this one would not be differentiable. It'd be where this denominator would equal 0, where we get division by 0. So this one does not have a derivative at 3. Well, we would not be able to apply the mean value theorem if 3 is in our interval. Luckily, our interval is outside of this. 3 is not within 4 through 9. So is it differentiable everywhere? No. Is it differentiable on our interval? Yes. All right, so let's apply mean value theorem. Go through, do the same thing. What is our values on bottom? From 9 to 4, 9 minus 4. On top, we got to figure out what is our function at these values. So what's our function at 9? And what's our function at 4? If we plug in 9, we got ln 9 minus 3 is whatever natural log of 6 is. If we plug in 4, we get ln of 4 minus 3. ln of 1. ln of 1 is 0. So on top, we got natural log 6 minus 0. On the right, or on the left side, I mean, we want to put the derivative. We already found the derivative is x minus 3. So what do we get when we solve that? Well, the top is ln 6. The bottom, we get 5. Okay, we want to keep solving. We got a fraction equal to a fraction. We could cross multiply here and see what we get. If we cross multiply, 1 times 5 is 5. If we multiply the other side, we got ln 6 times the quantity x minus 3. We could divide by ln 6. And then finally add 3. So on our calculators, we want to go through, see what we get when we do that, and that should be the value. So if we take 5 divided by ln 6, close the parentheses when you do that, plus 3, we get the value. At about pretty close to 5.79 would be the value. That's where the actual slope equals the average slope. All right, last problem. This is another application of this mean value theorem. It says a car drives 200 miles in 3 hours. At some point, was the car traveling at least 60 miles per hour? Well, what was the average speed here? If you take 200 divided by 3 on your calculator, you can figure out what the average slope is. 200 divided by 3, 66.6 repeating. So was the car traveling at least 60 miles per hour? Mean value theorem says it had to at least have done this, been going this speed, 66.6 at some point. So was it traveling at least 60 miles per hour? Yes. It must have been going this 66.6 at least once. At some point, was the car traveling at least 65? Yeah, again, 66.6 is more than 65, so yep. At some point, was the car traveling at least 70 miles per hour? Now this one, we don't know. Maybe. It could have gone 70 miles per hour and then been going really slow at some points and still averaged out to be 66.6. We don't know on this one. Maybe it was, maybe it wasn't. We can't tell for sure. Here would be an application of it then. Should this person get a speeding ticket if the posted speed limit was 65 miles per hour? Yeah, we know this car at some point went 66.6 miles per hour according to mean value theorem. So did this car speed at some point? Slightly, but was the vehicle speeding? Yes. So mean value theorem would say yes, it must have been. All right, try those problems out from the assignment for tomorrow.